Acyl chlorides are extremely reactive, and that is because of the position of this electronegative chlorine atom here and this electronegative oxygen atom here, pulling electrons away from the carbon. And this results in the carbon being extremely electron deficient and susceptible to attack by nucleophiles. Typical nucleophile which will attack is a water molecule, and if we draw a water molecule, it has lone pair of electrons, two lone pairs of electrons, and the hydrogens, and we know that water itself is also very polar. And therefore the nuclear attack will begin with a pair of electrons from the oxygen atom attacking the carbon. So what in fact has happened is the oxygen is forming a new dated covalent bond, pair of electrons coming from the oxygen going to the carbon. This is unsustainable because there are now 1, 2, 3, 4, 5 covalent bonds around the carbon, and therefore a bond must break. The resulting bond that breaks is the pi bond between the carbon and the oxygen here. When the double bond breaks, a single sigma bond remains, and the oxygen now possesses another lone pair of electrons which have just been taken from the carbon and a negative charge. The chlorine at this point is still connected. The big mistake is to cleave the carbon-chlorine bond, but the carbon-chlorine bond at this point stays intact. Now, if water has attached by the oxygen, don't forget that there are still two hydrogens attached. And now that the oxygen has 3 bonds to counteract this negative charge here, we must have a positive charge on the oxygen system. This intermediate is formed as a result of nucleophilic addition. This intermediate here is not stable, and therefore, to retain stability, a pair of electrons present on the oxygen here will move back to reform the double bond of the carbonyl group. And now you can see there is a total of 1, 2, 3, 4, 5 bonds, again unsustainable. If this bond breaks, we end back up with the acyl chloride. However, the more likely scenario is for the carbon-chlorine bond to break, since now it's got the weakest bond energy than a carbon-oxygen bond. The carbon-chlorine bond is going to break because chlorine is more electronegative. The electron pair will move onto the chlorine atom. And notice that the electrons are flowing in exactly the same way. To complete this, you'll notice now that the hydrogen on the water can be removed by chlorine taking a proton, and therefore oxygen hydrogen bond will break. Notice the beauty of the electrons all flowing in exactly the same direction, all flowing in one direction. This next stage, because a small molecule is going to be lost, is called elimination. So the whole mechanism is nucleophilic addition elimination. Nucleophilic addition elimination. The final product, therefore, is the carbonyl group is reinstated. The chlorine has gone, and an OH from the water is added on. And what's come off is a molecule of hydrogen chloride. So when water is added to acyl chloride, you will see fumes of hydrogen chloride being evolved, which aren't that nice. And you'll also notice a vinegary smell as you'll notice that a carboxylic acid has also been made. If we take any nucleophile, the mechanism is identical. What we're going to look at now is another common nucleophile, and that is with ammonia. The ammonia molecule, just like water, is a nucleophile because it possesses a lone pair of electrons. What you try to do next is to write out the mechanism. What you should do next is to try to write out the mechanism for the nucleophilic attack of ammonia on an acyl chloride, and then check the video to see if you've got it correct. So what we're now going to do is we've got a general acyl chloride, and this time instead of water, the nucleophile is ammonia. Do not forget your dipole, and therefore the lone pair of electrons on the nitrogen will form a dative covalent bond, and we know that this is not sustainable because the carbon will now have 1, 2, 3, 4, 5 bonds. So the next step is for a pair of electrons to move on to the oxygen, exactly as it was in the mechanism above. Exactly the same mechanism. Don't be tempted for the chlorine to break off, so remember next to draw the nucleophilic addition intermediate. So the nucleophilic addition intermediate is the pi bond has broken, so negative charge, lone pair of electrons on the oxygen. The carbon-chlorine bond now is weakened. There's the rest of the molecule. And here is the ammonia, and there's your dative covalent bond. Exactly the same as when the water added, the nitrogen now has 4 bonds, and therefore to counteract this negative charge, the nitrogen gains a positive charge. Analogous to the reaction above, with water, now the carbon-chlorine bond breaks. Remember, it doesn't matter which way the clear arrow goes, as long as it's under the chlorine, and the chlorine will take a pair of electrons, will take a hydrogen atom, and therefore the bond must break here. So notice the electrons are all flowing in the same direction. Down from the double bond, from the chlorine, taking a hydrogen, and that bond breaks there. So this time, the resulting molecule is R, C double bond O, the chlorine has gone, and this time we have an NH plus the HCl, and our resulting molecule is this time an amide. You could then ask yourself, what's formed if an amine attacks an acyl chloride? Well, an amine is simply an organic derivative of ammonia. So here is a primary amine with its lone pair of electrons, and there is the alkyl group or aryl group. Exactly the same mechanism occurs. Here's your acyl chloride, lone pair of electrons will come from the nitrogen and attack that extremely electron deficient carbon. So make sure you put your dipole on the carbonyl group. An amine, here we have a primary amine, which is just an organic derivative of ammonia, where one of the hydrogens has been replaced by an alkyl or an aryl group. The mechanism is identical as with ammonia and with water. So you can spot the pattern. There is nothing new happening at all. There's our acyl chloride. Don't forget to put your dipole on there to show the very electron deficient carbon. And there's our chlorine. So the lone pair of electrons attach the electron deficient carbon. As usual, pi bond break. We then get our nucleophilic addition intermediate, where the oxygen got a single bond and a lone pair of electrons. Oops, so there's no lone pair of electrons. Chlorine is now more likely to leave than the nitrogen bond breaking. Don't forget the positive charge here. So there's the nucleophilic addition product. It's not stable, this intermediate, so a pair of electrons will come back down, reforming the pi bond. Electrons flow in the same direction onto the chlorine. Chlorine picks off a proton, which throws its electrons into nitrogen. Absolutely the same mechanism. This time, rather than just having an ordinary amide, however, we end up with a substituted amide. I'll call it R dash. So we now have a